Okay, hello everyone. I welcome you to the first virtual edition in the second half of 2020 of our Machine Learning in Healthcare meetup. We have gone now fully virtual and we set up a new infrastructure to broadcast to you. So I hope everything works fine. If not, then please excuse any little hiccups that you might experience. My name is Vince Madai. I'm the main organizer of the Machine Learning in Healthcare meetup that started out in Berlin, and just a few weeks pre-COVID started a chapter in Budapest, which due to COVID hasn't grown that big yet, but we hope that that's also going to change in the future. And we're also very happy to come back to also quite technical talks we have had in the last month. Also quite more abstract topics like AI in product healthcare development. And I'm actually very much looking forward to hear today about a very interesting topic that is a deep dive into machine learning in healthcare topic. I would like to call first also on the stage to say hello. Basically, first Adam, who is a co-organizer here in the Berlin chapter, and he will also say hello and say a few words about Iris, who will hold the talk in a few seconds.
Yes, I think the mic is mine now. Hi everyone, so I'm Adam Hilbert, co-organizer of the meetup. I'm also a colleague of Vince in many levels, present in research and machine learning as well. I'd like to introduce Iris Huijben. I'm really happy I'm pronouncing right. Who is a PhD student in the Eindhoven University of Technology and a biomedical diagnostics lab. She actually completed a BSc degree in theology and technology, and then had a master in electrical engineering. While she was specializing in digital signal processing and machine learning. So as you will see from the talk, this is a very fitting topic as well. During her PhD, she is working on different representation learnings for biosignals, and also she is conducting an internship in a really cool lab, which I know from firsthand in Qualcomm's AI research lab in Amsterdam, University of Amsterdam, supervised by really, at least in Europe, I would say worldwide renowned researchers in the field, for example, Qualcomm as well. So I think I would even give the stage to Iris. I'm really excited to hear about the topic you are presenting here. Maybe one last comment is that I'm gonna check the chat. You're all free to state your questions also during the presentation. I would say that we don't interrupt Iris, but at the end we can come back to the questions, and I'm happy to moderate that as well.
Cool. Okay. Welcome from my side as well, and Iris, the stage is yours. Thanks a lot.
Yeah, thanks for the introduction, guys. So this is a really interesting format of presenting, only against my screen, and I have no idea who is listening. But anyway, I assume people are listening to what I'm telling. So actually, let me start with a question. Since I assume you're all in machine learning engineers, or at least you're interested in machine learning, so you probably have some practical experience as well. And I assume you all know this feeling that you find a nice project, you find a nice data set to work with, and you try to store this whole data set on your hard drive, but it's full because your data set is too large. And even if you could store it, copying it to your hard drive take ages. So looking at the title of this presentation, Deep Probabilistic Subsampling for Task Adaptive Comfort Sensing with applications in MRI and medical ultrasound. You might wonder, what does my data have to do with the title of this presentation? So my name is Iris. I'm as already was introduced, I'm a PhD student in Eindhoven University of Technology. And the coming 45 minutes, I'll try to explain you how this title relates to your huge amounts of data. And this work is a joint work with Bastiaan Veling from the University of Amsterdam, Kees Jansen from Philips, which is also in Eindhoven. Massimo Misci is the professor of the Biomedical Diagnostic Lab, and Ruud van Sloen, assistant professor in this lab. So I already introduced the topic a bit, right? We have a lot of applications nowadays that are generating a lot of data, and transferring all this data is not easy, but also storing the data is not easy. And even if we could do that, if we could transfer it, applying digital processing is more like complex if we have more data, and requires better processing. So an example, let's look at an example, medical ultrasound imaging. The trend is to have like smaller transducers that are just small devices that we can click to our phones or tablets, and just transfer the data in real time to the tablet, make real-time images, and preferably the images should be high quality, high resolution, maybe even 3D images, all kind of things that we want nowadays, but we are sometimes limited by the hardware. Storing and transferring all this data is just difficult. So what is actually causing these great amounts of data? Because if we don't know what the cause is, we can't solve the issue. So if we look at the left side, let me see if I have a pointer. Yeah. So here we have a certain application, maybe MRI, ultrasound, whatever. This generates data, and somewhere in the digital system, we do something with the data. And nowadays, while processes are getting more automated, we try to do something with the data, often with the system and not manually. So what happens here in the arrow in between? For the people here that are in electrical engineering, you probably noticed that we have physical data, physical signals, which are continuous signals. And to use those physical signals in a digital system, we have to digitize them. And that's what we do with an ADC, an analog to digital converter. So how does this work? So we have this continuous physical signal, and we're going to sample over time. We're going to take measurements at certain points in time, which looks like this. And then the digital representation that your system sees is actually this. And to go one step further, in practice, we also often quantize the data, which means that we quantize the values that we measure. But for now, let's only focus on the timestamps at which we sample the data. So how do we actually know how often we have to take a sample? So this is something that we have known for a long time. Mr. Nyquist came up with this theory, and he proved that if we sample with at least twice the highest frequency that's in the signal, we can reconstruct the signal. So we're able to fully reconstruct it. So let's see what happens if we don't do that. If we have this signal and we take too few samples, then if we try to reconstruct the signal, we might reconstruct it like this. And this is what we call aliasing. And you probably have heard about the term, but if you didn't, you've probably seen these kind of effects. So this is the actual jacket of the actor. But due to aliasing, you see low frequencies existing here. So this is exactly the effect of what happened here. The sampling was too low compared to what's needed to fully reconstruct the signal. In this case, the signal is an image, and an image is just a two-dimensional signal, right? So it's exactly the same theory behind it. So the first conclusion about the introduction of this presentation is that many medical, but actually all digital applications create a lot of data. And we cannot just reduce the amount of samples that we take, because then we get aliasing. So then you might think, okay, but why don't we just then do some data compression, right? So data compression would look like this. We sample the signal, and within the digital domain, we compress to squeeze it into fewer bits, and then we can still do the same system task. And all conventional data compression techniques that we know, for example, principal component analysis, independent component analysis, video codecs, in machine learning with autoencoders, they all operate on data that has already been discretized, so in the digital domain. But what if we could compress the data already at the stage where we actually gather the digital data? So at the point where we sample the data. And this is what we call sub-Nyquist sampling. So sub-Nyquist sampling means we sample below the famous Nyquist rate, which for years have given us how would you say, guarantees to reconstruct the signal if we sample with this frequency. So what is the advantage of actually moving from compression in the digital domain to compression in the ADC? Because for now I didn't mention why we want to do this. So there are, looking in the medical domain, because we're here in the medical meetup, there are several advantages of compression at the source, at sampling. Because, for example, look at MRI. If we take fewer samples, we can make quicker scans because we scan fewer lines, for example, so the scan can be quicker. And a quicker scan means fewer motion artifacts, cheaper scans, etc. In ultrasound imaging, think about these small devices that we have nowadays. They rely on a good battery, so more samples in the analog to digital converter draws more battery. So because the ADC is responsible for a lot of power usage in your system typically. Also, as I said already, if we have fewer samples, we require a lower bandwidth to send over all the data. And it might even allow, for example, on-device computing, like we see here in the image, where we can directly create an image on a tablet or on a smartphone, for example. And another example is CT imaging, where every transmission comes with harmful radiation for the body. So the fewer transmissions we make, which is implied by fewer samples we want to take, the less radiation we project on the body. So we can add another line here. We would like to take fewer samples, but doing that naively is not an option. However, we see that reducing samples can give more benefits than only compressing in the digital domain. So then the question is, can we really not go below the Nyquist rate? And it turns out, actually, we can. Since around 2004-5, the framework of compressed sensing was introduced by these 4 names that by now have been known by a lot of people, and it's a really a great framework that many people adopted. And so first I want to introduce you a bit to compressed sensing, in case you don't know about it, before I'll introduce our method. So in compressed sensing, abbreviated with CS, we have a certain measurement model. So we have a certain signal X, for example, an ultrasound signal. And we take measurements by psi, and the Y vector is our measurement vector. And in general, the psi matrix takes fewer samples, so it's m by n, where m is much smaller than n. So we really reduce the amount of data. So then the great question is, given this measurement matrix that causes sub-Nyquist measurements, can we still reconstruct X from the measurements Y? And it turns out, under certain assumptions, there are guarantees that we can do this with a negligibly small error. And these assumptions are the following. X should be sparse via a certain transform domain. So X itself doesn't have to be sparse, but in a certain transform, it should be sparse, which means that most of the samples are 0 and only few of the coefficients of the signal are non-zero. Also, there is an assumption on how the psi and inverse sparsifying matrix should be. They should adhere to the restricted isometric property. And intuitively, this means actually, you can see this in the drawing here on the right. What it intuitively means is that if we have an X element and we measure it using this matrix combination, then Y1 and Y2 should remain distant if the X's were distant as well. So remain with the isometry. So we have this measurement model. So how are we going to optimize it? This is actually your optimization problem, right? You measure Y and you try to reconstruct X hat. And since we made the assumption that X is sparse in a certain domain, we add the sparsity enforcing L1 penalty on Sx, and Sx was the sparse representation of X. So now we know that using converse sensing, we can actually reconstruct X from Y given certain assumptions. Given X is sparse, given that the measurement adheres to a certain property, and we often use iterative algorithms to solve it because there's no closed form solution. So we have the 3 properties of converse sensing. Sampling, and the sampling should adhere, as I said, to the restricted isometric property, the RIP property. And finding actually a sampling method and measurement matrix that complies here is maybe not the hardest part, but finding a measurement strategy that's also optimal for the task, for the system's task, or for the data is definitely not guaranteed by this property. Then we said, okay, we have to know that X is sparse in a certain domain, and we also have to know this domain. So we require knowledge of a sparsifying basis. And third, we have iterative signal reconstruction, which is in fact not so suitable for example, real-time signal reconstructions, for example, in ultrasound imaging, where we want to have real-time videos or images. So let's look at converse sensing in practice first. I took the example of MRI. And in MR imaging, we typically sample in the K space, which is actually a spatial Fourier domain. So we can represent it as F, the Fourier transform of X. That's the domain in which we sample. And we sample with subsampling matrix A in this case. So this is again our optimization problem. And again, as we saw before, we try to reconstruct the signal in a sparse domain. This is actually how it works for MRI, and we see since a year that Philips, which is super close to Eindhoven, in Eindhoven actually, that Philips actually came with an MRI scanner on the market in September 2019 that is actually using converse sensing to reduce the amount of samples in an MRI scan with a factor 2, and therefore almost reducing the scanning time by a factor 2. So it's great to see that the converse sensing framework, which is already there since 2004, is now being adopted in practice as well. So let's look at converse sensing in ultrasound. In ultrasound, we don't typically measure in a spatial Fourier domain. We measure radio frequency data, which is in itself not sparse. So there is sparse representation maybe, and the S minus 1 times XS here is the radio frequency data X that we actually measure in ultrasound. And to fulfill the property, the restricted isometric property here, But what is often done is that psi is chosen as a random projection matrix, like this. And we call this as if you take, you actually take linear measurements of X, because you combine all the elements in X, you multiply, matrix multiply it with this vector, so you linearly combine all the elements in X. And what does that mean? Suppose you want to subsample your ultrasound RF signal over time. It means that we have to linearly combine all the samples over from the past and maybe even from the future, which we don't even have yet, to make our measurements, which is not really feasible. If we would want to subsample, for example, channel arrays of the probe, we have to really in hardware wire all the channels such that we can linearly combine the measurements. So practically, this is not really feasible for ultrasound imaging. And besides, we don't actually really know in which domain ultrasound images are sparse. We can think about a wavelet domain, which we often use in MRI as well, but it doesn't give guarantees that it's sparse enough, actually. And also, as I already said, we are really interested in real-time imaging in ultrasound, and then an iterative signal reconstruction method is not really appropriate. So now I'm at the point of explaining the probabilistic subsampling, and I chose to explain the framework with the MRI example, hopefully to make it a bit less abstract and to give you an idea of how it actually works. So you saw this image before. We have the K-space of MRI. We sample it. That's AFX. And then we reconstruct it. And we said, okay, choosing the sampling, how to sample is not really easy. It's not straightforward. What's the best sampling pattern? And we guess often that, for example, discrete cosine transform or wavelet transform are the sparse basis for MR images. But if this is this really the case? And we rely on iterative reconstruction. So what if we change these elements in the typical computer sensing framework by data-driven methods, so machine learning models? So then we get a sampling model and we get a task model. And in the example of MRI, the task would be reconstruction, where we can think about segmentation, for example, if we're making an ultrasound scan and you want to segment certain tissue in the image. For example, if you make an ultrasound scan of a lung, nowadays we worked on segmenting the COVID markers, the COVID-19 markers in the lung. So you can think about a task model as any machine learning model that can do any medical task for you. Let's see what's coming next. Yes. So if we bring this together in a formula, it would look like this. We have the signal X, actually the K-space f of X, we measure in the Fourier domain. We subsample it by A. And to enforce that A is really a subsampling operation, it's a matrix that has 1, 1 per row, and the rest are zeros. So it actually exactly selects one element of the K-space. And then we have a function g of theta that we call the task model. And it's parameterized by theta because it's just the parameters of the neural network. And in this case, the task is reconstruction, x hat. So we propose to jointly learn the discrete sampling, so A, and the downstream task model, g theta. So let's start at the sampling model, and to see how it works. Suppose we have this K-space. It's the incoming data. We could see all these pixels in this case as n candidate coefficients. So n possible Fourier coefficients that we possibly would like to sample. And the task for us is now to learn which m out of n samples, of coefficients actually, are the most interesting ones to select for the given task of image reconstruction. So how do we do that? We could say, if we see every Fourier coefficient as if we train a probability value on each of the coefficients, so we train n probabilities, then we could draw from this distribution. So how does it look like? We have a categorical distribution with n class probabilities, actually a multinomial distribution, where each class probability represents a Fourier coefficient of this data, of this image. And then we're going to train the probability values for each Fourier coefficient. And then you would get something like this, for example. If we then draw samples from this multinomial distribution, we draw m samples from the distribution without replacement, then we can create a subsampling mask that looks like this, with exactly m coefficients selected. So let's start with the first thing first. How do we sample from a categorical or from a multinomial distribution? For that, we can use Gumbel-Max sampling, which is already a technique that is old, from 1954, as you see. And to show you first that it works and then how it works, I'll first have a short demo. Here we have an example multinomial distribution of 10 classes. So in our case, that would be a multinomial with n classes, and here we just have 10. And then I'm going to draw samples and sample realizations, actually. And the more realizations we draw, you see the more the histogram of the samples will follow the original distribution. Pay attention that the scale is a bit different. That's my fault. But you see that the shape of this histogram after a lot of Monte Carlo samples follows the original distribution. So that's the idea of Gumbel-Max sampling. So how does it work in math? I just introduced the class probabilities as P, and I don't know if you saw it here. If we take the logarithm of these class probabilities and we add some independent, identically independent distributed Gumbel noise samples, take the argmax of this, then we return with one sample from the distribution. It's one realization of the random variable that exactly follows this distribution. Why this works, I'm not gonna prove to you why this exactly follows this distribution. For now, you have to believe me that this is true, and that's why I show you the demo as well, to not dive too much into the math here. But I want to say one thing about the Gumbel noise, because maybe people haven't heard about it. The standard Gumbel noise, that's the one we use for the Gumbel-Max sampling, is a distribution that looks like this. And interestingly, just an interesting fact, you can create samples from the Gumbel distribution by twice the negative log of the uniform distribution. So you take a sample from uniform between 0 and 1, and then minus log, and you get a sample from the Gumbel distribution, which is actually a nice property that we often use in our code before Gumbel distribution was widely implemented in PyTorch and TensorFlow. So let me see about my story. Yeah, so here's where we were. We said, okay, we trained class probabilities, but to refine it a bit, we actually train the log probabilities, because it's always easier because logs are unconstrained. So we train unconstrained logits, as I call them. And from there, we can again just generate the sampling mask by Gumbel-Max sampling, as I just explained. Oh, yeah. But then the point is, now I tell you, okay, we train the log probabilities. And you might wonder, how do we train the log probabilities? Because what we know from typical backpropagation in neural network training is that we that we always have to go back propagate through all the functions back to the parameters that we try to optimize. And in this case, argmax is not a differentiable function. So how do we solve that? Now, luckily, in 2017, 2 papers from Madison and Young et al. Came up with this idea kind of at the same time. That's why there are 2 papers of 2 different groups. And they said, if we replace the argmax function by a softmax function, which is just a relaxation of the non-differentiable argmax function, we can actually relax this sampling procedure in a differentiable way. And it introduces an extra parameter here, for which for now I'll not go too much into detail. But this is a simple trick, and it's called Gumbel softmax sampling, to allow back propagation through the sampling procedure. And what we actually do is we use the hard sampling, the non-differentiable sampling, and the forward pass to ensure that we really feed task model with discrete samples, and to ensure that it really learns to deal with only a subset of the amount of data. And backwards, we use the relaxation to update the logics. So I hope you're all still here with me. But I don't have any feedback, so let's see in the questions afterwards. And one important thing to realize here is that once we trained the probability distribution, we can draw one realization of such a sampling mask with these M selected elements. And in many cases, we can just implement the sampling mask in hardware, which means that we can directly, as we started the story, we said we really want to subsample the data already at the sampling procedure. We don't want to first gather a lot of digital data and then compress it. We really want to reduce the sampling at the sampler. So what can we do once we get a realization A of a sampling mask? We can use it in a non-uniform ADC sampler, for example. Or in the specific example of ultrasound, we could make sparse transducer arrays, channel arrays. So you have, within your probe, you have this channel of transducers, and you can steer that at certain points in time, not all the channels are firing a pulse. Only part of the channels is doing that. So that also ensures that you have to sample fewer incoming data again. But also over time, for example, we can skip a whole time frame. If we learn to subsample over time, we can skip a whole time frame in hardware. This is for MRI. For MRI, for example, we can normally we typically define a scan sequence. And if we learned how the scan sequence is most optimal for the task of reconstruction, for example, we program a sparse scan sequence, and in this way, the hardware is really ensuring to take fewer samples. And in CT imaging, we just reduce the amount of transmit events according to the scheme that we learned, and therefore also reducing the radiation, as I said in the beginning. So, recap about the general framework. So this is what we saw. We have the incoming data, we have a sampling model that we learn, and we have a task model that we learn to perform a certain task, and we jointly learn this. And now we know how to learn the sampling by using a relaxation in the backwards pass. We can use discrete sampling patterns. So, as I said, this task model can be generic. It is not related to how we learn sampling. Because we can learn, for example, any function of x. We can learn to predict any function of x. It doesn't necessarily have to be reconstruction. We can learn classification, segmentation, whatever machine learning task you want to learn. And this is typically what we do with machine learning. The only extra thing we add is the sampling model here that we also learn. And since this task model is can have any task, you can just use the neural network architecture that you prefer or that's most suitable for the task. And as we use different models in different experiments, for now I'll first jump to the results before I'll dive a bit deeper in the task model. So here's some results where we did use deep probabilistic sampling for MRI. And what do we see here? We see an example image, actually the one I used throughout the whole presentation, of a fully sampled case space. So this would be the input of the sampling operation. And a perfectly reconstructed image looks like this, and this is the zoom area. So if we randomly sample only 1.2% of the samples, so 1.2% is really few samples, and we really pushed here to show how far we can get as long as we have a good model. If we randomly sample, that's actually what comprehensive theory suggests. With our model, we're not able to reconstruct the image. Then we tested with low-pass sampling. As the case space is actually a spatial Fourier domain, this means that we sample the low frequencies. And what do we see? We actually see exactly what you expect. Here, the whole line is gone because of blurring, because we didn't sample the high frequencies. And what happens in DPS? The learned log probabilities took this form, which is really interesting. Because if you look well, okay, it's a bit small, but if you maybe you see it, that there are kind of diagonal lines here, which is interesting because it's also the symmetry that you see also in the Fourier spectrum. So it learned, red is higher actually, and blue is lower. So it learned to have more importance in the lower regime, but not simply the low pass filtering as we did here, but also some diagonal lines here. And making one realization of that resulted in this sampling pattern here. And now we see really remarkably that we only sampled 1.2%, which is really low. If you look at the compressed sensing solution that Philips brought to the market, they sampled 50%, half of it. So we really pushed here. And still we are here able, for example, to reconstruct this line. Of course, not perfect here, not perfect with the ground truth, but for a bit higher sampling patterns, it would definitely become much better again. But it's really remarkable that we can do this here with only few samples, but just chosen at the correct locations, at the optimal locations for this task, for this data. And to show you that DPS is not just learning to sample where the Fourier spectrum is highest, because that would be like the easy catch, of course. As a nice example here of an MNIST experiment, where we made the setup exactly the same. We sample in Fourier domain, so these are the Fourier domains of each corresponding image. We learn sampling log probabilities, and then we draw a sampling mask. And if we draw multiple of those sampling masks in a Monte Carlo procedure, and we plot them here on top of each other, what do we see? The central frequencies, the low frequencies, are never being selected, even though the power in the Fourier spectra is really high there. And this is exactly the case because our task was classification. So think about it. If all the digits have like high power in the low frequency and you want to classify them, then it makes no sense to sample that value actually, to sample that low frequency coefficient. So we really see that DPS is not just learning the power spectrum, it's really learning which samples are most interesting for the task. Another example where we experimented with learned sampling for ultrasound imaging. And here we had the task of Doppler reconstruction. And Doppler is what you see here in colors. Actually, blue means movement away from you, and red means movement towards me. The input of the model here is radio frequency data, ultrasound data. We learned to subsample it, and we wanted to learn subsampling over time. So just skipping entire frames. And this is typically difficult for Doppler prediction because you need to predict movement. In this case, it was a heart. To predict movement, you need the relations among frames to predict this movement. So if you just uniformly downscale the frames that you sample, you might get errors in how you predict the movement. So what do we compare here? We said, okay, we're going to just fix uniformly subsample here the frames over time. So we only take 1/4 of the frames in a uniform fashion. And for reconstruction, we use the typical reconstruction method that is typically used in our case to make the crime truth, but also in the medical situation. And what do we see? It's totally not working out at all. So the fact that we uniformly subsample the frames, the conventional method cannot deal with that. And then, not surprisingly, if we uniformly sample but train the task model on the uniform sampled grid, we are already doing much better. This is the power of machine learning, right? So the conventional reconstruction cannot deal with this. The task model learns to adapt to the new subsampling pattern. Though, if we not only train the task model, but also train the sampling jointly, they can both adapt to each other. And then we see, for example, within the circle, you see that here we can reconstruct some movement information that here just got lost. So we actually see that learning jointly the sampling and the task model really helps. And interestingly, look here at how the sampling pattern learned to be. You see all kind of groups of two frames, like one frame in between, like 2 frames close to each other, then kind of a gap, and then 2 frames. That's kind of the structure you see. And it's really interesting that it does that, because if you take a group of frames together, it can get some movement information from these frames and capture really the high frequency information, and then wait a bit to capture low frequency information, and then again a group of frames to capture some high frequency information. And to show that this sampling pattern was really task adaptive, we also did this experiment for the task of B-mode grayscale reconstruction. And here you see the sampling pattern that it learned, and actually it learned to be almost uniform, which is really makes sense, because if you're in ultrasound, you know that creating such a grayscale B-mode image doesn't rely on relations among frames, but it relies only on within the frame. So there's no inter-frame relation here, and actually it also shows that it learned this by learning almost a uniform pattern. So let me recap. We saw this slide before, but we saw it for compressed sensing. And now I filled it in for using DPS, the probabilistic subsampling, and the learned task model. So now sampling is not something we have to guess how can we sample, and does it actually adhere to this restricted isometry property. No, we just learn it in a task and data dependent way. And now we don't need to have any knowledge about the sparse varying basis of the signal. And another advantage is, once a neural network is trained and you have new data coming in, which is already in hardware subsampled, you feed it to your task model. And without iterations, you get your task reconstruction. I have here some slides a bit more in depth about the task model, but I see I'm presenting now for 40 minutes, so I'll see if I can be a bit quicker here. But to give you a slight idea of how we designed the task model, our ultrasound experiment was the first experiment we did in the first paper we wrote about this DPS. So there we just use a simple, plain convolutional model with maybe only 5 or 6 layers, really basic actually. And then we went to MRI, and we realized we probably needed better task models to get good reconstructions. Let's see. And to explain you how we design this task model, I'll first start with a toy example where we have a sparse signal in time domain, and we sample in a frequency domain related to how we do this in MRI. And we have again the task model. We learn sampling again, so the A matrix, the subsampling matrix, we learn again. And here we see the frequency representation, and the red lines indicate how DPS learned to sample. And using the task model, we were able to reconstruct the sparse signal. That's the set. So how does this typically work in comfort sensing? I told you about iterative algorithms. So one of these iterative algorithms for sparse signal reconstruction is iterative shrinkage and thresholding, also abbreviated as ISTA. And what does it do? You have your measurement here. We make a gradient step. Everything here inside the curly brackets is nothing less or more than steepest gradient descent. You probably recognize it. And then after your steepest gradient descent step, you make a mapping to your proximal, to a space in which you know your signal lives. And in our case, we know that the signal that we try to reconstruct should be sparse. So our proximal operator here is the soft thresholding operator, as we know that this enforces sparsity. So this is a toy example, but actually, we in practice, the signal that we try to reconstruct is, for example, not sparse, but in another manifold, and we don't know exactly what this manifold is. So this ISTA algorithm is actually a special case of a proximal gradient algorithm, where we have the gradient step and a proximal mapping to a manifold. And if we rewrite this a bit, we can visualize it as a block diagram. And what did we recognize here? If you're into neural networks, into recurrent neural networks, you see that this looks like a recurrent neural network cell, right? So we can unfold this recurrence in a feed-forward neural network. Something wrong here. Unfold it in a feed-forward neural network and learn some of the steps within this network. So what we do here is, instead of just learning for the task model just a stack of convolutional layers, we learn here the step size, the subsampling matrix. That's what we already did, right? And we learn, in this case, a proximal mapping, because we are uncertain about the manifold in which an MRI image should live, right? So we learn it in terms of convolutional layers. So looking back at this pipeline that you saw before, now we know how we designed actually the task model in this way, using this recurrence of known signal processing iterative algorithms. And the good thing is, if we compare the use of, for this story example, we compare the fully connected task model with the model-based task model, as I just explained. And because the model-based task model has knowledge about the sampling procedure, because the sample matrix A is part of the model, we see that convergence happens much faster. It's much easier for the task model to adapt to different sampling strategies during training. So to summarize, we want to sample sub-Nyquist. We want to do this in medical imaging because we get quicker scans. We reduce the amount of power by the ADC sampler. We need lower bandwidth. We can do on-device computing. in CT imaging, we reduce the amount of radiation. And on top of that, in general, it reduces the necessary bandwidth and eases storage of data. So this is what we saw. The general framework was, the arrows moved. We have a sampling model A, and we jointly train it with a task model to predict any machine learning task that we want to achieve. And by jointly learning this, we can sub-Nyquist sample some data without introducing aliasing, and then we have the data which is actually able to fulfill the task that we want to do. So some of the key messages, there was a lot of information, I guess. Reducing sampling rates has multiple advantages for any application, but also for medical applications. And we saw that DPS facilitates task and data-dependent sampling patterns. We do not have to know anything about the sparsifying basis of the signal. And once we train the model, we do not need any iterations to reconstruct the task. And as a last message, I would like to tell that DPS is actually can be generalized to a representation learning method or learning subset selection. That's actually how you can frame DPS in the big world of machine learning. So I hope you remember this image from the second slide. And I think we made a great step into learning how we can reduce these vast amounts of data in such a way that we only extract the information that we really need for the task that we're trying to achieve. Thank you.
Thank you, Iris. That was a really, really nice presentation, and thanks a lot. And I really want to say that I think works like these are really the hidden champions of machine learning in healthcare. It's not another bad bias model on bad COVID data that goes finds the headlines every 4 days. The impact on healthcare is just unfortunately for most laymen, the impact on healthcare of works like these is just not very clear. But as you touched upon it, but really faster scans with less motion open up the possibility to scan more people, to scan them in higher quality, and this is actually then becomes machine learning for machine learning, because this higher quality then again can be used for classification tasks, for segmentation tasks, and makes that easier. So again, this is ML for ML in health. So this is beautiful.
Yeah.
So thanks a lot. So Adam will do now a Q&A. Sorry, by the way, for the introduction banner that was left for in the beginning for the first minutes. Then we got rid of that. But to compensate for that, I have a nice Q&A banner for you. And Adam will take over. I actually have a few questions, but let's see first if we have questions from the audience. Maybe Adam has one, and Adam takes over for the Q&A. Yes. Thanks again from my side again.
Yes, first of all, great presentation. I do have written up quite some questions. First, then I will read one from the YouTube chat, because we had one as well from Marton Görög, who is, I guess, from the name is from Hungary. Question is that right that we train 2 networks, but the first sampler network is not input dependent? Only task dependent, so we don't need to run that model for each measurement, but the second net is needed. I see.
It's a good question. I don't exactly understand what you mean by for each measurement. I think you mean each data point in the data set. So it's slightly true what you said. So we have 2 networks, the sampling network and the task network, and which can be seen as a concatenation together in one machine learning model. So as a whole, it just works as any machine learning model. So we choose the subsampling factor. For example, we say, okay, we have this MRI data set and we want first to subsample with a factor 4 and reconstruct this task. So as soon as you decided on the subsampling factor and the task, and therefore the task model design, it's one model that you train as any machine learning model. So you feed the data set in batches until the whole model is trained. So it's in that sense not different than any other model. I think what he refers to is what is different per measurement. So whether we have to train a different model per image. We exploit actually the machine learning idea of like you train the global best likelihood for the data distribution of your training set. So that's exactly the same as in any machine learning program. We train the best sampling method for this whole training distribution.
Yes. Yeah, also as I understood that basically on the sampling side, you have to, for data inclusions, you have to be paying attention on the actual data type you're working with, and then on the task network, you can focus on what is actually defined as the task and what contributes there most. Yes, question answered, was confirmed on the chat.
Okay.
I don't see any more questions yet, so maybe I take my privilege in being live and I go for my question. I actually had a really I don't know, interesting idea. I just had a flashback a little bit from my times from Amsterdam, where I had so I was also studying in the University of Amsterdam. I had a guy also the same master who was working on actually acceleration of MRI scans with recurrent inference machines, also from the lab of Max Planck. I don't know if you, so this is like a group really close to you and Bas as well. Have you compared their methods? I know that they only focused on the acceleration, so I think from subsampled K space to reconstruction, and defined it as an inverse problem as it is, and use these recurrent inference machines there.
Yeah, sorry, go ahead.
But I think, so as I understood now, your solution is kind of like a generalization of that whole idea, and a little bit also broader in the sense that it's not only the reconstruction, which can be a task, but also the sampling part. I was just curious if you somehow compared their work, or at least heard in the MRI domain.
No, it's actually a good question. In principle, we focused on the sampling part, and that's also what I meant by the task model can be any model choice. So for MRI, we saw we just couldn't get away with just stacking some convolutions, so we took a more model-based approach, and that's why we used that. But still, for now, the focus was really on learning how to sample and dealing also with the fact that with scaling, for example, with the fact that in MR images that are like high resolution K spaces, so you have like a lot of parameters if you want to train probabilities for all different coefficients. We try to solve those challenges there. And for now, we didn't focus much more on the task model. But I agree that inverse problems, it is in fact an inverse problem in compressed sensing reconstruction. And really researching better dedicated task models for specific tasks or for specific data is definitely only helping the performance of DPS, because of the sampling part, because the sampling relies on, so the sampling part of the model gives a subset of the samples to the task model, and then the task model does something with it. But the better the task model works, also the easier it is again for the sampling model to determine which samples have to grow in their probabilities and which should lower. So definitely it's interesting, yeah. But until now we didn't do it. Yeah.
I would also think that even though the like both of the parts are quite important, for example, acceleration as well. So they both play a role in it. Have you benchmarked anything like on the time consumption when you're modeling comparison of something?
You mean in terms of how much speed you gain by how much acceleration? We don't have actual values of how much speed we gain, as we did not yet implement the learned sampling patterns in a real MR scanner. But what I know, I'm really not an MR expert, but what I know about this is at least that if you sample with a factor, subsample with a factor 2, you don't get a factor 2 in speed up because there's other overhead, and that's also what you see in the Philips real world implementation, where they subsample with factor 2 and they get nearly factor 2 speed up. But for now we mainly benchmark with other sampling strategies instead of looking at. So we fixed the subsampling rate, or the acceleration rate, what's often called, and then compare the performance of the task.
Yeah.
And actually now we're working on really nice direction in which we make the sampling conditions, because now we sample, like we learn a fixed sampling pattern for the whole data distribution. But you can imagine that when a new image or signals coming in, the sampling might want to adapt to it. And there we're also making more extensive comparisons indeed to other baselines of adaptive sampling, adaptive subset selections, these kind of things.
Nice, sounds good. Vince, maybe do you want to something? I can go on with questions.
Actually, my question was exactly that was just answered. If there was any there were pilot results, how much it could help, and but as you just said, it's not implemented yet. Adam, I suggest you choose the last question from your list for the last question of today.
Okay,
the most interesting last question of your list. Go on.
Yeah, maybe just on application that you already, and I don't know how close of a cooperation this is with Philips. Of course, you don't tell us what you can't tell. I'm just curious because this could be quite a big impact on like mobile devices as well, or scanners, for example, in like mobile stroke units, for example. But of course, in some countries where there are big distances between care centers, talking about stroke centers, there it can be crucial. And such a method, I again go back to the acceleration. It can be just crucial in the implementation of the whole scenario. That it just makes it possible to make scans basically on smaller data constraints as well, but also in time-wise. Have you heard about any work, or have you gotten any good feedback about this on your work?
So you mean on using speed up scanners in remote areas?
Yes. So for example, the potential application in mobile scanners.
And with mobile scanners, you mean like these ultrasound scanners, for example, the small ones. Yeah. In terms of like, I just know that these definitely in ultrasound are more familiar than in other imaging techniques, but I just know that indeed in ultrasound we really see the development of these small devices in which it's really necessary to, if you want to have real-time reconstruction, you have to be able to do the task model computing on device, on this phone or on the iPad. But I'm not working for Philips, so I have no idea what they're doing. But actually, I know that there is some interest in, we lately, I'm not working for Philips, I'm collaborating with them. So lately we were working on also a machine learning segmentation model for lung ultrasound scans. And then they say, okay, it would be super nice if we have these small devices, right, like the butterfly probe, to just implement these kind of networks on device. So there's really, and I know also other companies in Eindhoven are working on this, like there's really the request to have like smaller networks that we can really run on small devices, and also look at wearables, for example, like all these wearables. And if you want to have your information on the screen of your smartwatch, then it would be super nice if you can do the computing there. And yeah, so I don't really have a concrete example now of where we worked in terms of on-device computing, but I just know that there is also a lot of research going on like quantization of networks, even binary neural nets, to make them more efficient for on-device computing. So yeah, I think it's super promising if you can already like first reduce your networks by model pruning, quantizing your weights, etc. But at the other side, also like reduce your data that you actually are processing in your task model. I mean, it all helps, right, to make the future come closer.
Yeah, 100%.
Absolutely. I think that was a really good words for the end. Bring the future closer. I really think these techniques will frog leap imaging and make it even more important than it is today. Iris, thanks a lot again for your great talk and for talking at our meetup. Adam, thanks for helping out, and of course to all the other organizers of machine learning in healthcare. Zsófi, who is running the chapter in Budapest. Thanks, of course, to all that stayed with us for so long, but also for those who have dropped out after the talk and couldn't stay for the Q&A, and hope to see you next time. Thank you very much. Bye-bye.
Yeah, thank you.
Thank you.